Alrighty, guys, can you hear me?
Yes, we can hear you.
How are we doing?
I'm doing good, thank you.
So we're getting closer to the end of the semester, and the way that it's going to go in this course is the hope is for everybody to pick their project, and then start thinking about it, and start reading some of these references that are related to your project in the syllabus. And so what's going to happen with the lectures is that it's going to taper down. We're not going to have as much new material in the lectures as we've had before spring break. The homework, there are going to be 6 sets of homeworks. So there'll be one homework. There'll be 2 more homeworks due here in April. I pushed the homework that was due tomorrow. I pushed that a week, but in principle, there should have been 4 homeworks due before spring breaks, and then 2 homeworks due after spring break. And this is all to give you guys some time to free up some of your time to work on these projects. That being said, I've gotten projects wishes for most of you, but there are still a few of you that have not. So if you could please let me know what your wishes are. I know we have some students in here too that don't take the course for credit, and for those students, it's completely up to you what you want to do. How much do you want to do? Do you want to have a written exam? A written project? Or do you want to do an oral presentation, or do you want to do no presentation? Or this is completely up to you. But for those of you that are taking the course for credit, there I do need to have your project wish soon, so we can I can be sure that you all picked it and you can all get started on it. In practical terms, what this is going to mean is that instead of spending 3 hours or almost 3 hours on the lectures, there's going to be less material, and there'll be some time then for you guys to start asking questions. There'll also be a few times in April where I have to end the lectures on the shorter end, because I have 2 meetings on 2 consecutive Thursdays that I need to attend. So this, again, it will give you more time to work on these projects. And of course, we still have office hours with the TA on Thursdays and Fridays, and with me on Friday morning. Okay, so with that said, are there any questions before we get started? So they're doing construction right outside my office here. So you're going to hear some banging out there, and this is because you're digging up the road, and you've been doing that for a few weeks. And then today it's right outside my window, so you'll hear them out there. So today, what I had in mind is we should finish our copulars. We were supposed to have this finished up before spring break, but we're going to finish our copulars. So this is going to take a little bit of time. So what we need to do here is we have these examples, and then there is a result which was used very heavily in when it came to CDO modeling. There's a monotonicity result. If you ever are to use copulars, and you also use the theoretical result related to copulars, chances are you're going to be using this monotonicity result. This was used heavily back in the days when it came to CDO, CDOs that we talked about before. And then the next big topic is going to be the finite difference. Finite difference methods. And then this is going to be, I just posted this homework. It's going to be in your homework number 5. And today what we're going to be looking at is, we're going to start with the simpler case of ODEs. Right, so the copulars, we talked about them before spring break. We will redo some of that material here in the next half an hour or so. There's not a homework related on copulars. I didn't put that in there. There will be like finite difference, what we're going to be doing the next few weeks. This is all in homework 5. So the last topic of the semester. So we're going to be doing this here for a while, and then the last topic of the semester will be American options. This is ultimately what we in your homework say. This is like, so we'll do this here for about 2 weeks. And then we'll do this thing here for 2 weeks. Okay, so let's finish up the copulars. Start there. Right, so recall that C, which goes from 0, 1, say to the power I, into 0, 1. This is a copular. If you can find U1 up to UI, such that well, the first one is that the probability of UI less than U is equal to U. This is for any U between 0 and 1, and for any I, let's put these commas there, for any I between 1 and I. So the U's are uniform. And 2, if I look at the joint distribution, so the probability that U1 is less than U1, all the way up to UI is less than little UI. If you want to compute that, well, I'll evaluate the function at U1 up to UI. So we're going to be looking at, we have discussed examples. So the normal is the most important one. You can see up here, this has to do with uniform distributions, right? So we're going to say, let me take a vector X. So this is a multidimensional object. Let's say, let's say I take a multidimensional normal. So that's going to have a mean of mean and variances. So the mean, let me put a 0 for the mean, and then the variance. Let's do a the one that is often being used, or was often being used about CDOs, was this flat correlation matrix. So on the diagonal, you would have ones, and then off the diagonal, you would have a correlation parameter rho for a correlation and people will take it to be positive. So we see from this that if I look at the covariance between xi and xj, you have zero mean. So this here is this here is going to be what? This is going to be the expectation of xi, xj, because there's no, the expectation of the individual ones would be zero. This here is going to be my rho. And so unless rho is equal to 0, xi and xj are dependent. Because you know, for jointly normals, being independent is the same thing as being uncorrelated. So this is the result we're using here. This is, so here we use a result for jointly normals. We also use a result for jointly normals, which says that independence is equivalent to zero correlation. And as always, when I teach this stuff, and I probably already told you guys this multiple times, it is crucial here that there is this word jointly normals. It's not enough just to have normals. You have to be jointly normal for this result to be true. Okay, so what does it have to do with calculus? Well, we know this trick that that if you say, so if we let f be the standard normal distribution function, so f of x, you integrate the density 1 over root 2 pi, and then an integral from minus infinity to x, e to the minus y squared over 2 dy. X is in R. Then what is it we know? Well, if I define ui to be f composed with x, I write to the ith coordinate in my normal vector up here. If I do this and I look at the probability, then that ui is less than, but this here is going to be a number. This function up here will look like to the left it goes to 0, and then it goes up to 1. Right, so this ui, this is something that takes values between 0 and 1. This here is my f. So this here is a number that takes values between 0 and 1, and is a random variable because x is a random variable. So I can ask, what is this probability? Well, then what I do is I plug it in. All of you have done this calculation here at some point with me or in another course. So I'm just reviewing. I once, years ago, when I was teaching a course on probability, there was a student who raised his hand and he said, can we please do this calculation in every single class? He said, this is something that he found very confusing. And so what I started doing after his comment was to slip this argument in here in as many lectures as possible. So if you're getting fed up looking at it, it's a good thing, because then you don't have to worry about it anymore. And if you still find it confusing, then we'll keep going over it. You have had it in the homework. You probably had it in other classes as well. So you transform in this case, it's a normal by its distribution, and I'm claiming you're going to get a uniform. And so when you look at this probability, what you can do is you can move f to the other side, and f here is strictly increasing. So it has an inverse, and that inverse is also going to be strictly increasing. So you're going to end up here with an f inverse of u. And then you use that this is the distribution, right? The xi's are standard normal. Like the individual xi is going to be having a mean of 0. And a variance, that's going to be 1 because that's on the diagonal. So, so when I transform f here, when I take xi and stick it into its distribution function, I'm going to get a uniform because this probability here, this is exactly f of f inverse of ui. And this is ui. Right, so ui here is uniform. This random variable here, this is uniform. Because, and then you do the calculation. And it's this argument here that the student years ago asked if we could please do some more in class, and so I did it here one more time. So what we did was we took these jointly normals. Individually, the standard normals, but they are dependent, right? Because we have this correlation parameter. And so what we did was we transformed them. So we got uniforms. And now the normal copular is the joint distribution of u1, which is equal to f of x1 up to ui, which is by definition the same function f, right? Because they're all standard normal. So the normal copular, this is the joint distribution of these uniforms, right? So we can write out what that is. So C of u1 up to ui, this is the probability that u1 is less than u1 up to ui less than ui, and we plug it in. This is P of f of x1 less than u1 up to f of xi less than ui. And if you want, we can express this here in terms of the joint normal of the multidimensional normal distribution. So we can do that by moving f here to the other side. Then we'll get that this is f1 less than, what will we get here? F minus 1 of u1 up to xi less than f minus 1 of ui. Right, so this here is the joint distribution. This is the joint distribution function of this x, which is x1 evaluated at the point x being f minus 1 of u1 up to f minus 1 of ui. So that's how we get the, this is the abstract description of the Gaussian copula. So the normal copula, a lot of people call this the Gaussian. So also call it the Gaussian. This is something we talked a little bit about before, but are there any questions on what we had on these few slides? So one thing that we also talked about, but let me just go through it one more time. Like so we can simulate U1 up to UI by, and then we write down the recipe. How do we simulate from this Gaussian copula? So step number one is let's say we want so step number one could be to generate independent normals. So let me call that Z. So that will be the Z that has so independent, and I should say standard normals. So start by generating independent standard normals. So we can do that. We've done that in class in earlier homework. And then to get the correct dependent structure, you factor out. So factor out this volatility matrix. That was the one we had. This here is my volatility matrix, variance matrix. This guy here. So row off the diagonal and ones on the diagonal. So we write that as 1, 1, 1, 1, and then put row outside. Factor out this in a Cholesky factorization. Right, so you write this here as A transpose, and you want A, this one here, you want this to be lower, triangular. So maybe if you just recall an example, just for example, this was something we tested out in class. If I do the two-dimensional case, if I write sigma as just a two-dimensional case, I'll have one, I'll have a row, I have my one, then I want to factor it out. Then I'll write A should be 1 row and then 0. And here I'll get root 1 minus row. I think that one works. Let's just double check it. So let's just do a sanity check here. If I do A transpose, A transpose, this will give me 1, 0, row, 1 minus row. This would probably be a squared times, and then you transpose it. So you keep the diagonal. And you put a row up there, and you put a 0 down there. What will we get? We get the first row times the first column, that'll be a 1. You get the first row times the second column, that'll be a row. Then you'll do the second row times the first column, that'll give me a row. And then you'll do the second row and the second column. This will give me row squared plus root 1 minus row squared. So this will give me 1 row, and then you factor out all that stuff here, you get row squared plus 1 minus row squared. And it'll cancel out, you get this is exactly your sigma. So you factor this out in the Cholesky factorization. So that was step number 2. And then step number 3 is to write your x, right? Remember that's your big vector of x1 down to xi. You're going to define this to be the lower triangular times the standard normals. Then this here is going to have the right variance covariance structure. And so you can simulate these x's here. And so to get the ui's, so you start out by simulating the z's, and then you plug it into this formula here that's going to give you the x's, and then you're going to get the ui's simply by transforming with the standard normal distribution function. And these here would be samples. These will give you samples. Of the Gaussian copula. Are there any questions or comments on this part? This is something that we have been over. We also looked at numerics related to this at some point, but that's how we would go about generating these uniforms that have this Gaussian dependent structure. So this was that was the normal Gaussian. The normal was the Gaussian copula. The other one I want to talk about today is this family that we started by talking about last time called the Archimedean family. This is used less, but people do know what it is in the industry. So I want you guys to know about it too. So another example is the Archimedean. The Archimedean copulas. We talked a little bit about that last time, but let me just tell you how do you simulate from the Archimedean? How do you simulate from a given Archimedean copula? So recall what an Archimedean copula is. You need this function. So here the starting point is you take a generator. So a function phi goes from 0 to 1, goes from 0 to 1 into 0 to infinity. So note that they are included here, such that there should be some properties. The first one will be that it starts out at infinity. Phi of 0 is equal to plus infinity. Then it goes down to 0. And it's strictly decreasing and convex. Strictly decreasing and convex. So it looks like this. It's at 0. At 0 it blows off to infinity, and then it ends out here at 1. It looks like this. This is my phi. And then the Archimedean copula, so the copula corresponding to phi, right? So phi, this is what's called the generator. The copula corresponding to phi is this function c of u. Let's put the indices downstairs. Ui, this is given by, so here you have phi inverse applied to, and then you sum up phi of ui. And so far, this is just that's the definition of what it means to be an Archimedean copula. You need these properties up here to make sure that this here gives you indeed a distribution function. So with uniform marginals. So what are some good examples, and how do you simulate the uniforms that has this dependent structure from these Archimedean copulas? And let me take you through that. So there are two main examples that everybody cites. The first one is the Clayton copula. Here, 5x is given as x to the minus theta minus 1 for some parameter theta. I think here you take theta to be positive. So if I am to write it out in the two-dimensional case, we should try to do that. So if I write out in the two-dimensional case, so when I is equal to 2, I will get the copula. This would be u1 to the minus theta plus u2 to the minus theta minus 1, everything to the minus 1 over theta. And the Gumbel, which is the other copula that people talk about when you talk about the Archimedean family, the Gumbel copula. The Gumbel copula, the phi function is a little bit different. Phi of x has the form what is it, minus log of x to the power of theta, and here I think you want to have theta bigger than 1. And so if I write out in the two-dimensional case, what would the Gumbel look like? So it's something with logs. We're probably going to get an exponential minus log u1 power theta plus minus log u2 power theta. Well, make sure that my thetas are the right spot. So we need one here, one there, and then everything to the power of 1 over theta, and then close. So there are other Archimedean families, but Clayton and Gumbel, these are the ones that people typically refer to when you talk about examples of the Archimedean family. And so how to sample, right? So how do you simulate? How to sample u1 up to ui from these from the Archimedean family. From a given and how do you sample u1 up to ui from a given Archimedean copula? But you have these distribution functions, but how do you sample? And it turns out that there is a not too complicated way of doing this, and that's what I want to show you. We looked at the pictures before spring break on how to. I showed you that it's possible to do it, but I didn't go into any details, and so I want to show you some details about how to sample from, say, these two copulars here. And it's due to what's called, referred to as Marshall and Alkin's trick. So it starts out by something that seems not related, but of course it ends up being very related. So you start by saying, so say that you have a random variable, we call it y. It goes from omega and is positive. Say that this random variable has Laplace, has Laplace transform so it's this exponent. The Laplace transform, right? You have a non-negative random variable, so the Laplace transform, you put a minus t times y. That's your Laplace transform of the random variable. And say it has the Laplace transform that miraculously ends up being this generator inverse evaluated at t. Right, this here is a number between 0 and 1 because y is positive, t is a positive number. T is a positive number. Right, so phi inverse, what does that go from? Well, phi goes from phi's domain is 0 to 1, codomain is a positive number, so the inverse goes from positive numbers and then into 0 to 1. So that's why you have the inverse here. So say that you can find a random variable that has this Laplace transform. Then Marshall and Alkin will tell you how to simulate. So then there's a method. Then there's then you can simulate. Then we can simulate. We can generate samples. Then we can simulate. Then we can simulate from the corresponding copula. In the way that we do it, you start by saying, so just as for the normal, there's a procedure. So the first step is sample a y, sample y. So this can be hard, but you have the Laplace transform. So in theory, you can invert this and you can figure out what the distribution of y is. So let me just write down here what the, in the Gumbel case, then y is what's called alpha stable. And in the Clayton, the distribution you need there is the gamma. This is the gamma distribution. When you look at this inverse function, so you have given phi, and like the generator is always given when you're dealing with Archimedean copulars, and so you need to invert it and recognize what this Laplace transform is. And in these two cases we looked at, one is stable and one is gamma. So you sample that y. This y here is called the mixer. This is called the mixer. And some people also call it frailty. or the frailty variable. So you sample that guy, and then you sample V1 up to VI independent, and independent of Y. So you sample independent random variables, independent of Y, and they are going to be uniforms on 0, 1. So you need to be able to sample a total of I plus 1. Right? You have 1 here, and you have I more here. They're all going to be independent. Y is going to have a complicated distribution depending on which one you're in. The V's are always just going to be independent, and they're going to be uniform. And then the magic happens in the last case. In the last step, you're just going to define this UI using the ingredients you had before, and the formula is as follows. This is minus 1 over Y log of VI. The claim is that this thing here has the right distribution. And it's quite a process, right? I mean, if you want to sample from, say, these two copulars here, if you want to do Clayton, if you want to do Gumbel, what you have to be able to do is grab something from a stable, grab something from a gamma, and then grab independent, put them together, mix them together according to this formula, and then voila, it works. So proof that this works. But we need to prove that the probability of U1 less than U1 all the way up to UI less than UI, and this is really equal to the correct copula, right? And it's that copula that is generated by phi. So let's do that. So prove that this actually works. And how would we go about doing it? Well, we'll start out. Keep in mind that the Y and the V's, they are independent, right? The UI is of course not going to be independent because this Y appears everywhere. Like every single UI has the Y in it. The V's and the Y's, they're not independent. So the way to get around this is to condition on Y. Because as soon as you're given what Y is, you're going to have independence. So it's an application of the independence lemma. It's yet another application of the independence lemma. So by the independence lemma, this is a result that you guys have seen used both by me and probably also in other courses like 6.2.2. You've seen this independence lemma being used in many different settings. And here's yet another one. But so what we do is we're interested in this probability up there. We're interested in this probability up here. And the way to do it, we should start by conditioning on Y. So let's do that first. Given by Y. Okay, so we can insert what the UIs are given by. Let's do that. So this here would be phi. This will be phi inverse of minus 1 over Y log VI less than U1 all the way up to the last one. So phi inverse minus 1 over Y log BK capital. This should not be I. This was the first one, right? So there should be no I here. This should be number 1. That should be a 1. That one there and that one there is the same. This was the last one. So this is less than U I given Y. And then what we'll do next is we'll move phi to the other side. So now we have to be a little bit careful because phi was a decreasing function. So when I move phi over, I'm going to flip the inequality. But I'm also going to move the minus y over. So I'm going to flip the inequality again. So there are 2 flips of the inequality here. There's a double flip. There's a double flip of the inequality. Like first, because phi is decreasing. And then second, because you have minus y and y is positive. So minus y is negative. So you have to flip it again. So we end up here with P of move phi over on the other side, you move minus y over on the other side, you move the exponential over on the other side, you get V1 is less than, and so what we get? We will get phi of ui minus a y and then exponential. This is again not ui, this is u1. And the last one will be the same, similar. Vi is less than exponential minus y phi of u capital I. And then you're given y. This was a double flip of the inequality. And now comes the independence lemma. The independence lemma says that, well, I know here that the y and the v's, they are independent. So what I'll do is I'll take out what I'm conditioning on. So I'll take out what I'm conditioning on. Let's call this for, say, x, phi of u1, vi, e to the minus, and then take out what you're conditioning on. And now we take the unconditional expectation. When we're done here, we replace the dummy with the random variable we're conditioning on. So this here is the independence lemma. This one here was the independence lemma. We have independence between the y and all the v's. So we replace the y with a dummy. Let's call that dummy little x. And we compute the unconditional expectation. And here we use that the independent. Here we'll use that v1 is independent of v2, and so on. Right, so these are all independent, so we're going to get the product. We're going to get the product of the individual probabilities, vi less than e to the minus x, phi of u i. When we're done computing all this stuff, we'll replace x with the random variable. Okay, so now we'll use what can we use? So this was the product. We have independence, we get the product. Now we have the individual probabilities, but individually we know that they're uniform. Here we'll use that vi is uniform. So what we'll have here will be the product. And what would it be? This probability, this will be the probability that a uniform is less than something is just that something. So this will be e to the minus x phi of ui. When we're done computing, we'll put x, y. We're almost at the end. We now have a product of exponentials. Product of exponentials is the same thing as the sum. So we'll put the sum in there. This here will be e to the minus x is a common factor. Here you go outside. You get the sum of phi of ui. And then we replace x with the dummy. We'll replace the dummy x with the mixer y. And then we're ultimately done because there's no more to compute here. We can just put y in there. This here will be e to the minus y, and then the sum phi of ui. So this was a long calculation to give us that the conditional probability was equal to this. And of course, if I want to get the unconditional one, I just take the expectation of both sides. So now we will get that the probability of u1 less than u1 up to u I less than ui. The unconditional probability, this is going to be to take expectation of this thing. This here will be equal to the expectation of what I have here. Okay, so can I compute what that expectation is? Well, this is where we're going to use. We're going to use that. This looks a lot like a Laplace transform. So we go down here and recognize that this here is the Laplace transform of y evaluated at that point, right? And then the assumption we're working under is that the Laplace transform is exactly phi minus 1. Right, so here we're going to use this. Here uses the this is the assumption that the Laplace transform e to the minus ty, this is exactly phi inverse of t. So this goes in here. So we'll see here, this is phi inverse and then evaluated at this sum here. But that was the formula. This was the formula for the Archimedean copula, which generate phi. Like, so this process here, it does work. Let me just show you the code from, we also looked at it last time, but let me just show you guys that code one more time so you can see that it is really not, this is not a huge burden to get to work. I'll just show you the lecture from last time. So this is why it's called MO, Marshall and Alkin's trick. Okay, so I'm hoping everybody can see us. We're doing the two-dimensional case. So we have I can only illustrate the two-dimensional case, and so we're looking at we're looking at the Gumbel case. And so what I need to do is I need to be able to sample this y, the mixer. So it turns out that in the Gumbel case, that the Laplace transform that you're looking at is going to be this alpha stable distribution we have here. And so you pull one of those, and then you just sample however many independent you need. In this case, we need 2 independent, sample at 2 independent, and I plug them into that crazy formula that we just proved was correct, and that will give me the copula. That will give me realizations of the copula. And so if I run this, lecture 8, I'll get a scatter plot, and you can see that this doesn't look like we have independence here, and we'll have U1 on the horizontal axis, and we'll have U2, samples of U2 on the vertical axis. So it's, as soon as you know what distribution to sample from, it's fairly easy to do this. You can to move between the different copulars. The only thing you have changed is what Y you're sampling from. So here now we're just sampling from, this is going to be the gamma distribution, and so switch it over, sample from the gamma, and you can see a similar plot, but it turns out that the Clayton copular has dependency down here, and the Gumbel one has dependency up in the upper right corner. So it's not terribly difficult to sample from Archimedean families. The only thing is you need to know what this mixer, that distribution that you need to generate the Y, you need to know what that is. So in these particular two cases, one is gamma, 1 over theta, the other one is stable alpha distribution. Also the parameters, there's some parameters in here, you need to know what those are. But given that you can figure that out, it's fast, it's fairly straightforward to simulate from them. Are there any questions about copulars up to this point? Are there any questions or comments up to this point? So the very last thing that I want to do before we stop talking about copulars is I want to show you this monotonicity result. This is if you are to work with copulars at some point in your life, you're going to be sampling them, and that's what we covered here. We looked at how to sample the normal. Chances are you're going to be sampling the normal copular. This is most likely what you will end up doing. And then there will be if there's some theoretical work that has to be done, and when you do this sampling, at some point you'll have to calibrate. And there is a result related. When people did the CDOs, at least first, second, and third to default that we talked about also before spring break, when you do calibration there, there's a result related to copulars that often was used, and the chances are that you're probably going to be using this result again if you ever are to discuss or use copulars. So let me end this a bit about copulars, talking about this. Okay, so this is what's called positive monotone transformations. Positive monotone transformations. Okay, so what is that? Well, what we do is, so we have our x. X is my x1 down to xi. Right, the marginals, this will be the f1 or fi of xi. The marginal distributions, they're given as the probability that xi is less than xi. These are the marginal distributions Write that out, the marginal distributions. Right, and then we get the uniforms. Then we get uniforms. This will be UI will be as before. You take the marginal distribution and compose it with the random variable xi. Right, and so then the copular will be C of U1 up to UI. This will simply just be the probability that U1 is less than U1 up to UI is less than UI. Or if you want, you can plug in the definition of these uniforms as we did before. Before we didn't have I dependence. We did the normal case because there were ones on the diagonal. Like there's an I here that we didn't have in the uniform case, and the reason we didn't have it in the uniform case was that here on the diagonal we just had a bunch of ones. But if you had variances here that would depend upon which I you were looking at, you'll get this I dependence. So I'm allowing for that here by having that I down here. So if you take the definition, we can plug that in here. We get F1 of x1 is less than U1 up to Fi of xi less than UI. Right, so we're starting with that. And now the result about positive monotone transformation is as follows. So now you're going to let these TIs. So I'm going to have a collection of functions. They are strictly increasing functions. So we have a bunch of functions that are strictly increasing. And then the claim is that if I look at x tilde, which is nothing else than Ti composed with xi. So I take all my random variables that I have up here, and I transform them with strictly increasing functions. Then the claim is that these guys, we also have copular C. They have the same copular. The tilde ones have exactly the same copular as the x's themselves have. And so that means that you can transform random variables by strictly monotone functions without disturbing the copular. Right? So let's give a proof of this. It's not that hard. It's just making sure that you get all the indices put in the right places. So just as before, we need marginal distributions. Okay, so we need marginals. Marginals, so I should call them maybe F tilde of xi. So this will be the probability. This will be the probability that x tilde I is less than xi. And we can plug in here what it is. This is x tilde, we put in the t instead. This is p of t I composed with xi. And then comes a place where I will move. So I will use now here that this is a strictly increasing function, right? So the inverse is also strictly increasing. I can move this thing to the other side without disturbing the inequality. This is the probability that xi is less than ti minus 1 of xi. And then I'll use that the marginal for x is denoted by f. So this here will be fi evaluated at this mess here, ti minus 1 of xi. So you can see what I mean when I say you have to keep the indices. Be careful when you put the indices, it easily gets messy. And then what is left is to calculate this distribution and check that it works. So finally, we should compute what is the probability of f tilde 1 composed with x tilde 1 less than u1, f tilde I composed with x tilde I less than ui. So we want to prove that this is equal to z. And so let's do that. Let's do that. So let's start by plugging in what x tilde is. So we'll get here that this is the probability of f tilde 1. X tilde was ti, t1 of x1 less than u1. Then I'll have f tilde I. Then I'll have ti xi less than u1. And then I'll plug in what is f tilde. F tilde was this function that we computed here. And so you see what happens is that when I take ti to go in there, the ti and the ti inverse, they cancel and just get f. So let's do that again. When I plug in f tilde, that was the thing I computed first, I'll get that this is fi ti inverse, but then I'll compose it with ti, they cancel, and I'll just get f composed with x. And this was the magic, because now I'm back to exactly the original expression. This was my copula. So it's not a difficult proof. The hardest part is to keep track of all the indices that they don't get messed up. Some of you might wonder, okay, so I talked about why this is important and how it was important when you did CDOs. And for those of you that are interested in this aspect, I put a little bit in there about this in the notes on copulas that I can get it to load. Okay, it won't load. So maybe I have it in here somewhere. There it goes. Come on. No, it won't load. I'll find it in here. Notes on copulas. So if we, for those of you that are interested in how one would go about using this sort of monotonicity result, it's over here at the end. So over here at the end. So here's the result that we just talked about, positive monotone transformations. It just says that the copula is invariant under these strictly increasing functions. And if you're interested in how to apply this result, so this has to do with getting the covariance matrix. This is something we talked about, trying to estimate empirically and so on. And then there is the general idea, and it comes out here that you're going to get one way to do this is going through Merton's what's called Merton's structural model, And there are a few slides or a few bullet points here on how to do that. And so you get it through these equations here. And this amounts to positive monotone transformations. And so if you can estimate a covariance matrix coming from equity data, and so here we're looking at Black-Scholes formula, then you can use that. So you're looking at returns for the stock, and this is the matrix that you'll be able to use to estimate this Gaussian copula that you need to price a default in these first, second, and third, and so on default contracts. So if you have such desires, if this is related to the project that you're doing, you will have to elaborate on these slides here to get this to work. Like, it's about estimating this covariance, and to do that properly, you're going to be needing this result on positive monotone transformations that I just showed you how to derive. Other than that, this concludes what I wanted to say about copulas. Talk quite a bit about them. I think next time I teach this class, we'll have a little homework on how to implement some of these copulas in a pricing. Are there other questions or comments about this? Any questions or comments about copulas so far? Otherwise, we're going to move on to, we're going to start talking about finite difference methods. So this is a completely different topic. So it'll be a little while before we get back to talking about simulation. There'll be over here towards the very end when we do American options. Like, for a while, we're going to be talking about a different numerical method. We won't be talking about simulation. Towards the very end of the section on American options, simulation is going to come back. We'll talk about how to use simulation to price American options, but not for a while. The next few weeks, there'll be nothing about Monte Carlo simulation. We'll look at other techniques to solve ODEs. Right, so the basic goal is, so we're going to start by ODEs. So numerical solution of ODEs. Right, so remember, an ODE has the form, you have your f prime, say of t, this is equal to some function applied to f of t and t. And then there's an initial point, say the initial point is t equal to 0, it's just some value that's given, let's call it a. So examples would be examples that you've already seen. The first one is the affine. So you look at f up here, f of f and t would just be say a of t plus b of t times f, where a and b, they are just say continuous functions. Continuous functions. Right, so if I take this f and plug it in here, I'll get the ODE that would look like f prime of t is equal to, I take my f, evaluate this capital F at f of t, I'll get at, bt, and then f of t. And then the initial point would be, say that. The one that you played with is the quadratic one. So this is what we call the Riccardi. So now we'll move up. We will move up to saying that not only is it affine, it's actually quadratic. So there's another function here. There's a z, and then you have your f squared term. And so that will give us, if we were to write out the general formula of here, this will be f prime would be a of t, b of t, f of t, plus c of t, f of t squared. And then you would have f of 0 is just a constant a. And so you should have just food for thought, just note. If I look at, so there could be explosions. Explosions are possible. Actually, you could try to look at say the Riccardi equation, where you would have f prime of t would be say 1 plus f squared. Say you started out just at 1. Try to consider this and try to consider f prime of t roughly the same. I'm just going to switch the sign over here with a minus sign. Right, there's a little innocent difference. This is just what I want you guys to note. Note the difference. So we're going to be looking at numerics for these two in just a little bit. We're going to be looking at numerics for these two just a little bit, and sometimes you can solve these ones in closed form. What's going to follow now is how do you numerically solve ODEs. This is a general form, and here are some specific ones. And one should just be mindful that some ODEs do not have solutions on arbitrary intervals, and here there is a potential problem, right? You can see here that when you start out at 1, right? So then the derivative at 0, what is it going to be? Well, it'll be 1 plus, and then f of 0. Okay, that would be 1 because that's where we started out, plus 1. So you're going to get f prime is going to be equal to 1 plus 1 plus 1. So that's f prime is going to be equal to 3. Right, so it's going to grow. Whereas over here, what's going to happen, right? So the bigger that f gets, the bigger this term here is going to get. And it's different down here when it starts out at 1. You can see when f gets to be big, this term here penalizes and it drives us back down. And you see when f hits 0 again, then these two terms here will vanish and f prime will be equal to 1. So it's going to bring it back up again. So this one here seems to be seems to have a better chance of not exploding. This one here, when f prime gets to be big, when f gets to be big, f prime gets to be even bigger. So the bigger f gets, the more, the higher the derivative is, the more f increases, right? So this one here can explode. This one here seems to have a better chance at not exploding. And then the only difference is this little sign you have here. So we are interested in solving ODEs of this sort numerically. So how does one do that? And in your homework, the reason I postponed it a little bit was that some of you might need to do that in your homework number 4. Okay, so that's the general form of the ODE, and let's talk about how one would go about doing this stuff. the starting point is what's called numerical differentiation. So we recall what a derivative is. If I'm looking at a derivative of u at some point x, right, that's defined as the limit as h goes to 0 of u of x plus h minus u of x divided by h. Right, so that's what the derivative is. And what we're going to be doing here is, so here are some examples of a numerical discretization. Okay, so here, h, when you compute the derivative, there's no requirement that h should be positive or negative. It just means that h has to go to 0. So here are some examples, and to make this more specific, I'm going to require here that h is positive, right? So you will see this limit, and then some people will put a plus here. This is when h approaches 0 from the positive side. Some people will write it as h and then down arrow to 0. So I'm interested in this limit here, in this visualization for h is positive. So we have a few suggestions on the table. So we have a forward. So this is denoted by d plus. So this is defined as u of x plus h minus u of x divided by h. That was the forward. So now h is positive. Keep this in mind. H is positive. You have the backward. This is the one with a minus. So then you're interested in u of x here, and then minus, and then it'll be u of x minus h divided by h. And then you have the center. This is denoted by dc, and then x, u of x. This will be, you do a mixture of these two. You have u of x plus h minus u of x minus h divided by 2h. But the thing that we're doing is, we have a function. We have a function like that. We're interested in approximating. We're sitting here at x, right? And the goal for us is to approximate the slope. This is my u. The goal here is for me to approximate the slope that I have here. And so what do I want to do is, in the first one, what I'm going to do is I'm going to look at it here, and then I'm going to go a little bit out, say h out here. And what I'll do is I'll approximate the slope here by that slope. So this here is the forward. I can also do the backward. So this is my x, and now I'll do the backward. This is x minus h. This here is x plus h. I'll do the backward. So again, the slope that I'm seeking to approximate is this one there. I'll go backward a little bit, and I'll approximate the slope by the tangent here. So this one here would be the backward. And of course, I could do the center. So I'm seeking to approximate the slope. This is my x. And what I'm going to do is I'm going to go in both directions. I'll go a little bit to the left. I'll go a little bit to the right. and then I'll look at the slope between these 2 points. This was the center. The question is, which of these ones should I use? Which is better, right? I have 3 suggestions. I should somehow be able to compare them. I would like to be able to compare them and say that this is better than the other one and give a precise answer for why. And you can see here that there's connection. Like this here looks a lot like maybe what we did with an explicit Euler. This here looks like an implicit Euler. This is just something to note here. This looks a lot like this explicit Euler. And this one here is the implicit Euler. But I mean, at this point, there's no Brownian motion, right? We're just talking about ODEs. We're not talking about the Euler scheme for simulating paths of SDEs, but we don't have anything for this one down here. So which one is better? We spent the last few minutes before the break on that question, which is better? And so what we're interested in here is we're interested in speed and we're interested in accuracy. Accuracy. Is that right? Accuracy. So we just recall notation. We call big O and little o a notation. I'm sure most of you have seen this before, but let me just refresh it. I'll be right here. F of x belongs to, and say a big O of g of x as x goes to 0 if what? Okay, so f of x belongs to big O of g if what? If there exists a number, little one, there exists a number, there exists a threshold, say x0, such that if I take f of x in absolute value, I'm going to get something that is less than my m is big. There exists a big number such that for small x's, I get something that is bounded by m times the absolute value of g for all x which are small. This was the big O. We write that f of x belongs to little o. Again, as x goes to 0, if I take the limit of x converging to 0 of the ratio, so I'll take f of x divided by g of x, and I'll get a 0. And this can be pretty, if you've not seen it before, this can be a bit confusing. Like, so there's a big O, there's a little o, and just to make it a bit more specific, maybe we can just look at some examples. If I have f of, say, x, this is my x squared. This belongs to O, big O of x, because what is it I need to do? This belongs to big O of x as x goes to 0. Because what? Because what is it I need to check? I need to take absolute value. Okay, so I take x squared. Is that bounded by m times absolute value of x? Well, this is the same thing as asking whether or not the absolute value is bounded by m, and this here is for x small. And then this is okay, right? Because I do have that. This will never work for x big, but it does work for x small. But if I switched it, and I would say, if I look at another example, if I look at f of x just being, say, x, and this does not belong to big O of, say, x squared for x going to 0. And the reason for that is, if I'm looking at absolute value of x, is this bounded by m times x squared? Well, this would be the same. This will be the same as requiring that 1 is less than the absolute value of x times m for x small, but this is false, right? Because when x is small, something small times m is going to be, it's not going to be bigger than 1, right? So f of x equal to x does not belong into this guy. We also, if you were to look at the little o, if I look at an example like f of x being x, this does not belong to little o of x for x going to 0. And the reason for that is, if I'm looking at x over x, this goes to 1 and not 0 as x goes to 0. So we won't have that either. Maybe the last example before we take a break could be to take something more lively. I take f of x. Say it's 6 times 4 to the x to the power 6 times x to the power 4 minus 2 to the times x to the power 3 plus 5. I take g of x just to be x to the power 4. Well, then I would have that f of x belongs to big O of g of x. Right, as now I'll take x to infinity. But when it grows in the, I'm interested in having it into the little o, it won't work. Does not belong there as x goes to plus infinity. Right, it grows at this x square rate, and so if I want it to be in little o, it should be the case that I'll take f divided by g, and I'll get something that goes to 0, but it does not. It goes to exactly 6. Right, you forget about these terms, and you just have x to the power 4 divided 6 times x to the power 4 divided by x to the power 4. It will give you a 6. So that doesn't work. Those are just some examples about what this little o and big O notation is. And so what, I think this is a good time to take a break. But what we want to do next is we have these, we have 3 suggestions on the table. And what we want to do next is we want to study how fast do these guys converge? How what is this O? It's going to be big O. What is their rate of convergence? Okay, let me stop here. Are there any questions before we take a little break? Any questions before we take a break? Okay, so let's take a break and then get back. Can you go over, this is Alice, can you go over little o again? Yeah, we can go over little o again. Let's do another sheet of little o. Do another sheet of little o. Right, so little o. Little o. So if I want to have f of x belonging to, say, little o of g of x, then what you need is that g here grows faster than f. So you can say this either as x goes to 0, for example. Then what you want to have is, I want to look at the limit as x and then goes to 0. And then you take the ratio f of x over g of x. You want g of x to go fast. Right, so you want this to be 0. Right, so if I looked at examples where I'll have f of x is equal to x to the power p, and say g of x is just x, then we could ask, when do we have x to the power p belonging to O of x as x goes to 0? Right, so you need to check, when do we have x to the power p divided by x? When does this go to 0? As x goes to 0. When do we have this? Well, this would amount to you can simplify this. This will be the same as asking, when do we have x to the power p minus 1 going to 0 as x goes to 0? When do we have that? This is when p is small, absolutely. And well, let's see. If I took p to be say 3. Take p to be 3, then this amounts to x squared. Does that go to 0 as x goes to 0? Well, no. Yes, sorry. This is okay? So it works for p equal to 3. If I do p equal to 4, then I'll get x to the power 3, right? Because it's 4 minus 1. This is also going to go to 0 as x goes to 0. And this is a yes. So how are we going to know? Well, if I take p to be, what could I take p to be? If I take it to be 0, if I take p to be 0, then what do I get? Then I'll get x to the minus 1. This is equal to 1 over x. Does that go to 0 as x goes to 0? So the answer here is no. So this will give you an idea about, like, when does it work? And you can contrast this with, so contrast with xp belonging to little o of x, but instead of having it go to 0 when x goes to 0, you could have it as x goes to, say, plus infinity. Right, so again, what we need to do is we need to have x to the power p divided by x, sorry. And I want this to go to 0. But now, instead of having it go to 0 as x goes to 0, I want to have it as x goes to plus infinity. So now what would happen is, if I take p equal to 0, that was the last case, right there I'll have I would have 1 over x. And does that go to 0 as x goes to plus infinity? Yeah, this time it works. This is true. And so if I pick one of the other ones, say p equal to 3, p equal to 3, what would I get? I'll get x squared. Does x squared go to 0 as x goes to plus infinity. And now the answer is it doesn't work. That also goes to plus infinity, right? So you can see it's important for where x moves to. You'll get p to 3, p to 4. This works when x goes to 0, but it does not work when you're looking at it to as x goes to plus infinity. And for us, so after the break, what matters to us is so for us we need x going to 0, and the reason is that it's going to be this h parameter. So I shouldn't write x here. I should write h. For us, we're going to be looking at this as h is small because we're looking at a derivative. So we'll be interested in these little o and big O when h is small, because we're going to be looking at a little time step here. I'm going to try to approximate this. We know when h goes to 0, that was the definition. When h goes to 0, we're going to get exactly the derivative here. The question is, as a function of h, how fast does this thing here converge to the correct derivative? Alice, did that help on the little o notation? Okay, let's take a break. Let's get back together here like 10 or so, and then go back on a different Zoom ID. Okay, I'll see you guys in a little bit.